In this video, we'll look at how to approximate derivatives with finite differences. The sample function is drawn here. It starts out at 0 at x equals 0, goes up to 1 meter per second at x equals 50 meters, and then goes back down to 0 at x equals 100 meters. So for the first half of this shown domain, the derivative is positive. The function is sloping upwards. The second half of the domain, the derivative is negative. We'll start by looking at very crude approximation of the derivatives. We're using very large differences between points. So I have the 3 points listed here, x equals 0, x equals 50, and x equals 100, where u goes from 0 to 1 to 0 meters per second. The delta u between the first 2 points is positive 1 meter per second. The corresponding delta x is positive 50 meters per second. So if I divide delta u by delta x, I have positive 1 over 50, 1 over seconds. That's my finite difference approximation of the derivative. But as you can see from the dotted line, it's not following the slope of the blue curve that closely. It's a rather crude approximation. Similarly, between the second 2 points, I have a delta u of negative 1 meter per second, and the delta x is the same, positive 50 meters per second. So delta u over delta x is negative 1/50th 1 over seconds. I've plotted this coarse finite difference approximation of the derivatives below in red. So for the first half of the domain, it's positive 0.02 1 over seconds. For the second half of the domain, it's negative 0.02 1 over seconds. Now we can look at more points along the blue curve in hopes of getting a better estimate of the derivative. So what you can see here is I have a spacing of 10 meters for all the x values. And along with that, I've given rough estimates of the u values as well. So it starts at 0, it goes on to 1, and then back to 0 again. But now we can see the intermediate values of 0.3, 0.5, 0.7, and 0.9. Now to calculate the finite difference approximations to the derivatives, we can proceed as before. It's just that we have a smaller delta x, or a smaller difference that we're looking at. So for instance, between 0 and 10 meters, u goes from 0 to 0.3. So the delta u is positive 0.3, and the delta x is positive 10. That means the first value of delta u over delta x is positive 0.03 1 over seconds. And for the next 3 values of delta u over delta x, I calculate 0.02 1 over seconds. They're not exactly the same actually, but from the precision that I can tell from this sketch, that's what I get. Closer to the maximum value of the u curve, the magnitude of the derivative gets smaller, and the finite difference approximation does too. So we have plus 0.01 1 over seconds on one side, and then it's negative 0.01 1 over seconds on the other. And then as we go farther along in the domain, we get negative 0.02 for the next 3 points, and then negative 0.03 as we get closer to x equals 100 meters. Looking at the lower graph, I've added in this new approximation of the derivatives in purple. So that's the new delta u delta x that corresponds to the column here. And what you can see is there is more resolution now compared to that first coarse estimate where our delta x was 50. Now I've shrunken down to a delta x of 10 meters, and our approximation of the derivative is getting better. It's not perfect, however. We can still see that there are many values that are the same, and it looks very stair-steppy. Calculating the derivative demands a lot of precision. One way to get that is to further reduce delta x. If I had picked delta x as 1 meter instead of 10 meters, then this curve would look better. Also, if I were more precise about the values that I picked off of the blue curve or the u curve, then that would help my finite difference approximations too. So a lesson here is that it takes a lot of precision to calculate the derivative. In this example, I actually know the analytical functions for both the original U-curve and its derivative. So the original U-curve is a sine curve with amplitude A, in this case 1 meter per second, and inside the sine, the argument is 2 pi x divided by L, where L is the wavelength, and in this case it's 200 meters. So we're really only seeing half of the waveform here. If you look below, I have du dx. I can calculate that analytically. So I take the derivative of sine, which is positive cosine, and then I have to apply the chain rule to the argument, and that's why we see the 2 pi divided by L out in front that's multiplying the amplitude A. So du dx is 2 pi A divided by L times cosine 2 pi x divided by L. And that's the orange curve that I've sketched in here. And you can see that that orange curve does go through the purple and red approximations of the derivatives made by finite differences, but they're definitely not the same. And that's because of the limited resolution and limited precision of which I calculated the finite differences. So as you're calculating derivatives by finite differences, I recommend paying attention to the resolution precision you use because the results will be very sensitive to that. And you want to make sure you get results that are refined enough for your purposes. Thank you. I hope that helps your math.